For those of you who don't know me, my name is Mike Anderson, and I'm from the PTR group. We are a company. We do a lot of consulting-related stuff. So we do a lot of work for NASA and robot arms, and we are just now, well, actually, over the past 2 years, we've been doing quite a bit in the IoT. And one of the significant things that you see about the actual edge devices, that is the distributed sensors. The distributed sensor environment is very, very different than what we're used to seeing in a standard Linux environment. There's no MMU, in many cases, there's no operating system. So how do you do development for platforms like the Cortex-M? And why do we even care about the Cortex-M? So let's take a look at some of those. This is PTR Group. We were founded in 2000. We do a lot of work with robotics for NASA, a lot of space platforms, flight software, offensive and defensive cyber operations. We won't get into the details on that one. But embedded software ports to RTOSs, Linux, things of that sort. So in the involvement in offensive and defensive cyber operations, we get into a lot of security related to the IoT. What things are vulnerable, where are they vulnerable, how are they vulnerable, what can you do to secure them, what can you do to exploit them, things of that sort. So I have been in this business now about 39 years in the embedded space. I developed part of VxWorks back in the day, so I've been in the RTOS business for a long time. I teach a lot of work, a lot of processes in terms of device drivers for Linux, porting Android to new platforms, things of that sort. And this is, actually, I've been speaking here at Embedded Linux Conference since 2007. So I actually have this session, this conference, I have 5 sessions. This one and the next one, of course, are the ones focusing on IoT. And then I have a bunch more of them for ELC as well. So what we're going to talk about in this particular session, we're going to talk about the ARM Cortex-M series and why it plays a role in the IoT. We'll focus on open source solutions. Now, why focus on open source solutions? We'll get into the details of that. And then what exactly is required for a complete open source solution? If you are a manufacturer and you're going to be building devices for the IoT, what do you have to have? What kind of tools do you have to have in order to be successful in building a device for the IoT that you're going to deploy and potentially sell millions of? We'll talk a little bit about the different compilers that are available to us in the open source community, and of course the IDEs, the development environments. We'll also we'll look at debugging solutions, what kinds of options are available to us for doing debugging, and then we'll summarize things up. I happen to have here an STM32. Hopefully we'll make it work, but we'll see. My little board here is a little upset with me at the moment. I did not sacrifice enough to the demo gods this morning when I was worshiping them. So we'll see how things work out. But why exactly? Now, this particular board is a Cortex-M4. We're going to talk a little bit about the Cortex series and what they have in them. ARM's processor cores, of course, they are constantly upgrading these things. We see that the ARM platform are broken into 3 basic classes. We have Cortex-A, Cortex-R, and Cortex-M. Gosh, it spells ARM. How about that? Cortex-A are application processors. These are the ones that you find typically in your cell phone. These are going to be Cortex-A15s, Cortex-A8s in the case of the BeagleBone Black, Cortex-A9s in the case of the new Raspberry Pis. Then there are the Cortex-R series platforms. Cortex-Rs are what they call real-time platforms. And by that they mean they have no cache. Since there's no cache on them, we don't have any variability in terms of its execution time, so we get very solid run times out of the Cortex-R. Where we see Cortex-R platforms used, we're actually seeing them in a lot of automotive applications, but they are also the primary processor attached to hard drives. So if you wondered how a hard drive does its cylinder head and sector to logical block address translation, that's how it does it. There's a little microprocessor in there, and it's typically a Cortex-R. Cortex-M are their energy-efficient microcontroller series. Now, the Cortex-M series actually ranges from the Cortex-M0 all the way up now to the Cortex-M7. They just introduced at ARM TechCon last November a V8M architecture. The V8M architecture incorporates trust zone into the Cortex-M. So by introducing the trust zone, that gives it basically a secure operating environment that can then be used to create hardened applications using these microcontrollers. Of course, one of the advantages that the Cortex-M has is it's a 32-bit microprocessor. Because it's a 32-bit processor, we don't have to worry about trying to find old versions of Microsoft tools in order to generate 8-bit code running on an 8051 or running on an HC11, 68HC11, or one of those other old 8-bit processors. I spent a lot of time writing assembly language for Z80s, 8080s, and 8085s. I don't really care to go back to that world anytime soon. So having the Cortex-M as a 32-bit processor means I can use modern tools to generate code. I don't have to keep that DOS 6.2 machine sitting around just so that I could run the tools to generate to run the compilers. There are over 175 different ARM licensees at the moment, and all of these guys are producing silicon. So when you compare the dollar value of ARM against Intel, for instance, Intel's a $54 billion a year company. Their processors are typically selling for $200, $300 for those processors. On the other hand, ARM has 175 different licensees, and ARM Limited themselves don't really generate much money because they're a fabless semiconductor house. So they produce licensing, they produce IP, they then sell that IP to other companies, and those other companies then produce the chips. If we were to take a look at total chip volume since 2005, ARM represents about 98% of all the chips that are sold since 2005. That is not lost on Intel. That's why Intel is focusing now on the Quark and all these other smaller processors to try and get their power consumption down. And power consumption becomes one of the major reasons why we use the Cortex-M, because the Cortex-M is capable of running off of a coin cell battery for 5 to 10 years. And that, of course, is a major plus for the IoT. We see the Cortex-M family, as I say, it ranges from the Cortex-M0, which runs about at 90 micron, through the Cortex-M0 Plus. That one on a typical 2032 based coin cell will run about 15 years. It is a very small processor, however, and so when we think about processors like the Cortex-M, we can't think in the same terms that we think of when we're dealing with Linux. There is no memory management unit. The Cortex-M0 typically has something on the order of 32K bytes worth of memory and maybe 128K bytes worth of flash. So the way it operates is significantly different than a typical Linux machine as well, because what we find in the Cortex-M is that the flash is executable flash. It's like NOR flash. It's not exactly NOR flash, but it's like NOR flash in the sense that we can load our program into that flash and we will execute completely out of the flash. The memory, the RAM that we have, is typically static RAM, and the RAM that we have in this case is simply used for scratchpad memory. It's used for the stack, it's used for dynamic variables, it's used for anything that has to change while the application runs. That's going to be stored in the SRAM, whereas the actual program itself will be stored in flash. The performance range that we have here, going from the Cortex-M0 Plus all the way up to the Cortex-M7, the Cortex-M7 was introduced a couple of years ago, and it is the big mamba of the Cortex series, Cortex-M series. It has on the order of, it has a cache, and that's one of the things that makes it different. Most of these processors don't have caches, but that one happens to have a cache. It also, if you look at the Cortex-M3, the M4, and the M7, they all have digital signal processing instructions in them. So this makes them ideal for doing things like MP3 players, Bluetooth speakers, things of that sort, where we actually start seeing them appear in consumer electronics items and consumer electronics goods. So the Cortex-M has a pretty broad selection of platforms. And we go from that really low power Cortex-M0, M0 Plus, up to the M7. The M7 will run off of battery as well. It just won't run as long because it tends to be much faster in terms of the processor cores themselves. The availability, of course, of DSP and digital signal processing instructions in the higher end M4 and M7 platforms gives me a lot of capability for low-cost infotainment. It also we'll see things like body electronics and audio processing, the headphones where you're doing noise cancellation in the headphones. Those are the kinds of things that lend themselves reasonably well to this digital signal processing kind of instruction set. Of course, they also have connectivity. Now, if we take a look at what's happening with Silicon Labs or what is it? Of course, Texas Instruments has their CC series. We also have the folks that tried to buy Atmel recently. Yeah, those guys. And there are a lot of these folks that are using radios. They create radios. They build radios. I asked a manufacturer, a Chinese manufacturer at one point in time, at what break-even point should we think about making our own radio versus using one that's already licensed by the FCC? And he goes, well, realistically, about 1 million units. If you're going to sell more than 1 million units, then it's probably worthwhile to try and make your own radio. If you're not going to sell at least 1 million units, don't even bother, because the FCC certification and all the hoops you have to jump through in order to get a radio approved for operation here in the United States is so large that it's just not worth it. So what this means is that a lot of companies are now selling integrated radio chipsets. And for the IoT, when we're talking about wireless interfaces, this is a big deal for us because it means that we then don't have to go through FCC certification. But these radios also have stacks built into them. So our small processor, our Cortex-M0, for instance, with 32 kbytes worth of RAM, trying to get a full TCP stack, something like that, that's just not going to fit all that well. It can. I mean, you can certainly do it, but you're really using a shoehorn to try and squeeze it in. On the other hand, we can put the stack in the radio and have the radio interface be a simple UART, SPI, or I2C, and then our small Cortex platform doesn't really have to do anything as far as the stack is concerned. We simply talk to the radio, and the radio implements the stack. So we also find this kind of interesting situation where people think automatically in terms of an RTOS. With a Cortex-M0 and any of the Cortex-M series parts, yes, you can run VxWorks, you can run Zephyr, you can run whatever it is, FreeRTOS, Contiki, all these different RTOSs are out there, Micrium's, MicroCOS, all these RTOSs are good RTOSs. They're good, solid products. But the reality is that when we're trying to do something at the very far edge, if we're trying to implement a sensor network where the only thing we're doing is we're sensing vibration in the turbine, or we're looking at the temperature or the humidity in the fields out in the middle of the San Joaquin Valley, we don't need a whole lot of capability. We don't need an RTOS. We don't need to pay for an RTOS. We don't need to spend the time trying to develop for an RTOS, because most of the manufacturers of these Cortex-M platforms are doing the best they can to enable us to run bare metal. It turns out that running bare metal on these platforms is not that hard. You don't have to use assembly language. There's assembly language in there, don't get me wrong, but you as a developer don't really have to think in terms of, oh, I have to understand the assembly language for the Cortex in order for me to be successful. I don't need to know thumb2 instruction set. I don't need to know any of those kinds of things, because I can just write it in a kind of a straight up C environment and or C++, and it will just work. So we're finding in many cases that there are a lot of these edge sensors that we don't need an operating system on. Operating systems add complexity. And if you're thinking in terms of security, the more complexity you have, the more likely you are to have screwed up somewhere along the line in the security piece. They present a larger attack surface. The larger the attack surface, the more likely you are to be hacked. So in the case of the edge devices, the smaller we can make them, the dumber we can make them smart, right? So we're trying to make a dumb device smart. But we want to make sure that we do that in such a way that we don't expose ourselves to a large amount of attack surface. Now, with the radios out there, the radios have got Bluetooth, they've got Zigbee, they've got 802.15.4, they've got 6LoWPAN. They have all these different protocols already built into them. You just buy the module, you plug it into the UART, and wham, you've got connectivity. It's not that complicated, fortunately. So in the realm of the Cortex-M, we often, if we were to go to Embedded Systems Conference or one of these other shows, we're going to see people like Kyle and IAR and Green Hills, and they're going to be telling you, oh, you need to buy my development tools to do work in the Cortex-M. And don't get me wrong, they're fine tools, but they're $5,000 a seat, and you have to renew it every year. And if you don't renew it, it turns into a pumpkin and your tools aren't any use to you anymore. So it's kind of like the crack dealer, right? The first one's kind of free, but once you buy in, you're stuck. You can't get out. And that's unfortunately what we see in some of these cases, not in all, but in many of the cases for the closed source development tools. They want to get you hooked. They want to get you thinking that you have to have their tool chains in order to be able to do development. And that's not the case at all. So, we see, for instance, they will make claims, oh, my compiler is 20% more efficient than the GNU compiler, or my compiler in this particular benchmark runs 10% faster than the GNU compiler. I've talked to the folks that do the GNU compiler for ARM, and it's ARM limited, the guys who make the chips. They tell me that if you find an example of another compiler that does better code than they can do on GCC, tell them, and they'll fix it. And I've actually had them do that a couple of times. So we have a case where we're not really stuck with a community that doesn't pay attention to us. We're actually working with a group of companies and people who make it their job to make open source tools work well on these platforms. So all of these tools, for instance, Kyle and IAR, they do support Windows. Some of them support OS X, but almost none of them support Linux. So if you want to run any of these tools on Linux, then you have to use a VM, and you have to run Windows on the VM, which is a bit annoying when I then have to pay for a copy of VMware and a copy of Windows, and then I got to make sure that I update it, and then Patch Tuesday comes out, and suddenly my development environment doesn't work anymore because Microsoft is updated. Now, Microsoft just recently announced that they're going to start working with Canonical to build Linux capabilities into Windows 10. There will actually be a bash shell prompt available in Windows 10. I'm curious to see how they're going to implement that. But it certainly is interesting that at least now Microsoft now announced they have their own Linux distribution. So there is a Microsoft Linux, and it runs on their Azure cloud systems. So, who knows? Microsoft may not be the great evil one that we used to expect, but we'll see what happens. So why focus on open source here? A lot of it has to do with the maker movement. The maker movement, people who are doing it themselves, they're trying to figure out how a particular platform works. They will see a board like this ST32 board here from ST Micro. It's $12 for this board. And there are those of us who just can't avoid buying something like that. It's like, what? I can buy an MSP 340 or 430 from Texas Instruments for $5? I'll buy it. What do I need it for? I don't know, but it's only $5, so I'll buy it anyway. And for those of us who find ourselves in that mode, it's really, we need to be able to do what we can. I mean, we bought this cheap platform. It's $5, but how do we make it work? And if it costs us a couple of $100 to make it work, well, then it's not worth it. We want to make sure that, yeah, we're cheap, okay, we bought the $5 board, but the reality is we don't want to spend $5,000 for a development environment. That's just silly. So what can we do to make that happen, be able to do development without having to invest large sums of money? Of course, we also see a lot of open source hardware. The Arduino, of course, is open source, the Raspberry Pi. We see BeagleBone Black. So these are open source designs. If we, as a manufacturer, decided that we wanted to build a device based on the BeagleBone Black, we could get the Gerbers off the open source environment and we could spin our own board. And there are lots of companies that do that. So this is, when we talk about open source hardware, we're really talking about how you can enable people to do quick designs. I've built an Arduino on a piece of paper, literally wired it on the piece of paper and had a working Arduino with just a few parts. So this is the kind of thing that enables the maker community, enables the do-it-yourselfers, the experimenters and people like that to be able to really create interesting devices. Things that may not have been interesting enough from an economic perspective for a manufacturer to build one of them, but you might be able to crank out 50, 60 of them for your friends, and that's kind of fun. So it's kind of a cool thing. But we're also seeing a lot of large corporations starting to embrace and transition to open source. We see Tizen, for instance, which is running the Linux kernel, but it's in your Samsung television sets. We see Android, we see Linux, of course, all over the place. So it really is more of a transition over to open source. And we have a lot of cases here where if you're a corporation who's decided you want to try and embrace open source, then you have to think of it in terms of the entire development model. And the development model, when we're looking at system development, we've got a lot of different phases. We've got the design phase. We've got tools that have to support these phases. We have to understand, how are we going to do development? Are we using Agile, Spiral, Waterfall? Waterfall's still used. NASA uses Waterfall all the time. So these old models haven't gone away. And if we're trying to do a full-up design that's going to be supported for 20, 30 years, we need to think about the documentation that has to go into the design to make it complete. And that's one of the other characteristics of the Internet of Things on the industrial side. The industrial side, we think in terms of decades for these devices to run. And this is not something that we're going to it's not going to be like a Fitbit, where you're going to sell one to somebody, and maybe two when they break the first one, but there's no residual sales of Fitbits to individual consumers. I mean, realistically, there isn't. So you have to think in terms of where is the money? Where's the revenue in the Internet of Things? Well, it turns out that the industrial side of the Internet of Things is about 3 times the size of the consumer side. And it's expected to be on the neighborhood of about $3 trillion in 2020. So there's a lot of money here if you can pull all the pieces together to make your Internet of Things design come together. And this also includes not only the development, the design, we have to edit, compile, debug, deploy. We have to be able to maintain the systems in the field. So there's a lot of stuff that goes into this whole process. Now, if we were to kind of go hardcore on open and trying to do everything as an open system, well, this is one way to do it. This one is a Novena open source laptop. It's a completely open source laptop. It has a quad-core ARM IMX6. It's a Cortex-A9. It runs Ubuntu or Debian Linux, either one. And it is a way to do it. I mean, it's like $1,200 for these things, but it's open source BIOS, open source everything. The hardware is open source. You can do daughter boards for it. Everything is open source. It's a really cool solution, and I know a couple of people who have one of these things, and they really like it. But the reality is that most of us probably aren't going to go that far. When we talk about open source, you go, well, yeah, I've got my laptop here, and my laptop is relatively cheap and very powerful, so why would I go to the trouble of building another one based on completely different CPU architecture? I mean, I get that, and that's a reasonable thing, but realize that you're under the control of the BIOS, and the BIOS you have no visibility of, so you don't know if the secure BIOS that you got from this foreign manufacturer isn't, in fact, phoning home to let them know that something's up. I've actually seen this. We bought some brand new computers. Usually when I'm testing things, I put it inside of a sandbox, and I make sure that it doesn't try to phone home. So I start screwing around with time in the system to see if it chirps back out. And sure enough, it contacted China, or tried to contact China. And when I asked the manufacturer why it tried to contact China, they go, oh, well, we were just checking to make sure there was no BIOS updates. They go, oh, yeah, right, okay, yeah, nope, let's get this equipment out of here, please. We don't want it. So operating system choices, and of course, Linux is the obvious choice for a lot of these systems. It's running in over 1 billion devices. They're called Android phones. So Linux is around and has been around for some time, and it's not going to go away anytime soon. Certainly, when we're dealing with development environments, we don't really think of Android as a development platform. It's a target platform. We don't think of iOS as a development platform either. So when we're thinking about development platforms, we're really talking about Linux, Windows, OS X, and some of the BSD variants. Those are all potential development environments for us. We're going to limit our discussion here to Linux, Windows, and OS X. We will mention the BSD variants every now and then, but usually we're not really seeing a whole lot of people doing development on top of BSD. They're using them as routers and servers, but they're not really doing heavy development on top of them for Internet of Things applications at least. So starting at the very design, in many cases we're using Unified Modeling Language, UML, and for UML there are some open source tools for UML. Argo UML is one that's Java-based. It is cross-platform. It does, in fact, run on BSD Unix. But Star UML is another one. It runs Linux, Windows, and OS X. So we have the design tools out there. Now, realistically, these design tools are not terribly sophisticated. They represent UML, of course, but UML is 30 different diagrams. And they select a few that are the most commonly used diagrams, but they don't support the entire gamut of UML. But they support a significant subset of UML. So if you're really into UML design, then yes, there are some tools available for you. Source code control, another big one. Of course, those of us who have worked with Linux know Git, but the other flavor of that people will use is SVN, the subversion network. So either one of those is fine. I find that SVN works along the lines of clear case. So if you're a big corporation and you're used to using commercial source code control systems like clear case, then you find that, okay, it works kind of like clear case. There's a major server, main server, everybody checks code out, checks code back in. Git, on the other hand, is a completely distributed environment, and it works well for the Linux community, and it works well for several other communities as well. Of course, we have GitHub, one of the major places where people store their repositories for source code. So Git, though, it uses a distributed concept. So that means that everybody has a complete copy. And if something fails, then that's okay. They can keep working on their copy, and then when the servers come back up again, they'll be able to do their commits. That was one of the things that kept Linux running when the servers got hacked. This was a few years ago. The servers got hacked in a big way, and it basically took Linux kernel development offline for about 2 or 3 weeks. But it didn't affect anybody because they all had their Git pulls, and they were able to continue doing work. And as soon as the servers came back up, they were able to do their merges, and everything kept going. So Git has some real advantages if you can kind of wrap your head around the distributed development environment associated with Git. Of course, compilation, we have 2 major compilers available in the open source community. LLVM, it's not an acronym, that's actually the name of the project. But we have, Bahan's not here. No, I don't see him in here. So actually we have the guy who heads up the program. He's the project. He's here, Bahan Webster. This is, right now, arguably one of the most widely distributed compilers on the planet because LLVM is built into every single copy of Android. So the thing that does the Android runtime, the just-in-time compilation in the earlier versions of Android, and now the Android runtime where it does the ahead-of-time compilation, that's all done with LLVM. So it's out there, it's being used, and it's being used effectively every single day. It is definitely an up-and-coming tool chain. It does have a fairly decent debugger, the LLDB debugger. It has static analyzers built into it, so it knows the integrated Clang static analyzer. So this is a pretty good tool chain. It is not the tool chain that we see used by the Linux kernel at this point, and nor is it the tool chain that we see used typically in Android, but certainly is an up-and-coming, to build Android, let's put it that way. It is an up-and-coming tool chain, certainly one that should be considered. It does a great job of producing ARM code. Of course, GCC is the tried and true. The GNU compiler collection, GCC, is really not one tool chain. It's really a back-end code generator with a whole bunch of different front ends available for it. So if you want to use C, C++, C++11, Ada, Objective-C, Java, Fortran, whatever, those are all available for GCC as front ends to the GCC backend that produces the code. Of course, all the code is licensed under the general public license, and there is a special exclusion inside of the GPL in the case of GCC, so that the code that's produced by GCC, even though it's GPL, a GPL compiler, it does not force you to use the GPL in the code that you produce. So there are some exclusions, some special rules with GCC that allow you to produce proprietary code if that's your goal. Obviously, as the open source community, we would rather you didn't do that, but there are some organizations who feel they have intellectual property that they want to protect. Therefore, we have a way of being able to do that, even using the GCC compiler. If you are still someone who speaks Fortran, NASA is looking for you, because it turns out that all those satellites, the one that just went by Pluto, it's programmed in Fortran, and they can't find anybody to do maintenance. So if you want to get into the maintenance business for satellites, which is kind of cool, not the satellite's cool, and the maintenance maybe not, but in any case, if you speak Fortran, they got a job for you. So it's definitely one of those, the GCC Fortran actually does a pretty decent job. Now, editors versus IDEs. This is a real religious topic. And you have the people who say VI and the others say Emacs, and that's the usual answer. And then they will duke it out in the middle of a field every now and then. The younger developers, of course, when we talk about using VI or Emacs or any of these command line based editors, we're viewed as dinosaurs. And realistically, they've been brought up on IDEs. So they've seen the integrated development environment. They've seen the, hey, I never have to leave Microsoft Studio, Windows Studio or Studio, what is C++ Studio, whatever it is. I don't have to leave that, and I can do edit, compile, debug, everything. I can do everything in it. Of course, the Emacs people say, well, we were really the first IDE because not only could you do that, you could also get mail and you could play games and other things inside of Emacs at the same time. All right, we won't argue that point with them. But for those who want pretty GUIs, there are a lot of options out there. Fortunately, it's not the only option. And that's the key thing. Those of folks who use GUIs, they think they're great to do development in. Until 3 o'clock in the morning rolls around, you want to check all your code out of the repository and compile it all and have it ready for you when it comes in the next morning. And guess what? IDE requires somebody to actually sit there and run it. So being able to script things is an important piece of a large-scale development project. So going back to the command line tools, allowing the user to use his, or his or her individual IDE preference, that's fine, as long as the tools and the code is bidirectional. That is, we can have it not only compiled from the command line, but we can also compile it from within the IDE. As long as we maintain that concept, then we have the ability to have the freedom of allowing somebody to use the GUI of their choice, but at the same time being able to run the compilers at 3 o'clock in the morning and recompile everything. So there are some major open source IDEs that are floating around. Of course, Eclipse is one of the big ones. CodeBlocks is one that's actually pretty popular. CodeBlocks runs in Linux and Windows, and it also does OS X, I think. And of course, the IDE from Arduino. It's not a terribly sophisticated IDE, but a lot of people know it, love it, and use it. It's written in Java. It's real simple to operate, and it runs in all of the platforms. It turns out the Arduino platform is built to use GCC, but you can also switch out Clang, so you can go to LLVM if you want to. Kdevelop, NetBeans, of course, that one's in Java. Kdevelop's written in C++. It's very fast. If you don't like Eclipse, because Eclipse is written in Java and it tends to be a little slow sometimes, then it turns out that Kdevelop's a great alternative for you. There's Ultimate++, which is licensed under the BSD license. All of these guys, all of these individual IDEs, the realistic perspective is, in Kucox and CodeLight, the reality is they all look alike. I mean, realistically, we haven't seen a new IDE since 1997. They all look alike. You've got a code window, you've got a navigator, you've got a thing that shows you all the variables in your particular piece of code. And they all look alike. They all pretty much work alike. And as a consequence, if you like IDEs, hey, knock yourself out. It's really a matter of personal preference here. Of course, IDEs written in Java tend to be more portable, but they also tend to be slower than the ones that are written in C and C++ native code. Still, all the major OS variants support a lot of these different flavors. So what we're going to do is we're going to specifically focus on the Eclipse side, because that's the one that so many manufacturers use. Texas Instruments uses it, ST Micro uses it. So many of the manufacturers use Eclipse. We're going to focus on Eclipse briefly here. We've tested this. I've had an opportunity to test this with the Luna release. I've just been testing it with the Mars .1 and .2 releases. It seems to work. The only thing I haven't figured out yet is the hookup for OpenOCD seems to be a little wonky with the Mars release. But nonetheless, they do have integration with both the Sager J-Link, and if you're thinking about JTags, and I'll be talking about ARM debugging, that will be on Wednesday, and the different options that are available for ARM debug. JTag, we have, of course, single wire debug, SWB, we have SDO, we have ITM, we have J-Link, we have ST-Link, we have all these different options that are available to us in ARM debug. It turns out kind of the universal standard there tends to be the Sager J-Link and its variants. So the J-Link itself, you can get an education version of the J-Link for $45, so it's not all that expensive. But if you get the one that has all the bells and whistles, the Ethernet interface and everything else associated with it, that's close to $1,000 for that one. But the nice thing about the J-Link and its brethren is that they speak GDB. So I can use any GDB front end that I like. So if I want to use DDD, or I want to use any of the other GDB front ends, if I want to use the GDB command line, I can still do it using that JTAG. So that's a very important capability. You don't have to run Windows to run the JTAG. And I have seen JTAGs that they only work in Windows. And it just bugs the living daylights out of me to have a Windows machine to debug my Linux box. There's just something wrong with that. All right. So there are a lot of templates for various Cortex-M platforms, including the ST Micro. The one that I'm using here is the STM32F and the Freescale series of Freedom boards. Those are all very cheap boards. So how do we get it set up? Well, first of all, you have to download Eclipse. That goes out to eclipse.org. You then get a hold of the ARM compiler. The ARM compiler, there are, of course, Linaro makes a great version of the ARM compiler, and that's the one I happen to use. I go out, I download the latest version of the ARM compiler. I think I'm running 4.9 at the moment. But they come out every quarter. They'll come up with an updated version of the ARM compiler. So again, it's free. Just download it and unzip it, basically. We'll start Eclipse, and then we'll tell it to install new software. And what we'll do is we'll point it, we'll point it to this Eclipse plugins here. The GNU ARM Eclipse plugins directory, this will then, is a repository. It will then figure out what version of Eclipse you're running and then pull down the correct version of the plugins for you. Then inside we'll have to select the plugin, so it comes up, you just do the little check mark and you install everything. You of course have to accept the licenses, and it does throw up a little security warning that says you're installing software that hasn't been signed by the Eclipse Foundation. Are you sure you want to do this? Well, that's up to you, but I usually say, yeah, go ahead, because I know where it came from and I know the folks who developed it. You then want to create a project. Now, in creating a project, you'll right-click in the project field and you'll then say, create a new project. And when you create a project, it has several different variants. It has Hello World type applications. It has blinky LED applications. And many of these applications will then target specific boards, whether it's the Kinetis series of boards from Freescale, the STM32 boards from STMicro. There are a number of different boards that are available to us. And then we will go through and we'll define what kind of platform it is. In this case, we're selecting a Cortex-M4, and we're going to run it without any operating system. We're going to run it bare metal in this example here. Then we set our tool chain and path. We've extracted our GNU compiler out into a location. We just need to tell the project where that compiler is located. Once we tell it where the compiler is located, it'll be able to find all the pieces associated with the GNU compiler. And then we will get our, on here on the right-hand side, we see the actual Eclipse front end. We'll then right-click and tell it to build, and it'll run off and run the compiler. Once we have the compiler, then we have various options for debugging. It turns out that in the way that the GNU compiler plugins work for Eclipse, for ARM, we have OpenOCD, which is the Open On-Chip Debug interface. OpenOCD is a really nice interface in the sense that, again, it uses the GNU front end, so it speaks GNU on the back side. It also supports like 70 different JTAG interfaces, including ones like the Bus Pirate and the Saley Logic Analyzer and the ST-Link. It also supports Sager J-Link and a lot of others. So it is a very, very interesting front end. It does run on Windows, runs on Mac OS X, also runs in Linux. And then it front ends all these debugger back ends. So the JTAG world, if you're not familiar with how JTAGs operate, it is a hardware debugger. Basically, it takes control of the chip and stops the chip in a particular cycle. We can then start single-stepping through either in assembly language or in C source code. So we have the option to do that. And JTAGs will cost anywhere from $50 to $20,000, depending on what kind of features you get. JTAGs for the x86, typically $15,000 for the x86. But when you ask the manufacturer, there's only 2 manufacturers in the world that make a JTAG for the x86. And when you ask them why it's so expensive, they go, who needs it? The motherboard manufacturers, okay, that's maybe 50 people, 50 companies. And then the BIOS manufacturers, which is only about 10. So when you think about the market of how you're going to recoup your investment to try and build a JTAG interface, there really isn't much of a market out there. So the prices of those JTAGs go through the roof. On the other hand, the ARM JTAGs, typically 50 to 100 bucks, you can get a pretty decent JTAG. It'll allow you to burn flash, it'll allow you to program the board, it'll allow you to single step and do debugging. All that sort of stuff will just work with OpenOCD. So our Cortex-M series processors, we're likely to see a lot of them in the IoT. Of course, size, weight, and power are the major considerations as to why we would be driven to the Cortex-M. The problem is that because there's 175 different manufacturers, the question becomes, which one do you pick? And a lot of it depends on what you're trying to accomplish. If you don't need audio processing, then you don't need the Cortex-M4 or the M7. If you don't, because you don't need the digital signal processing instructions. Now, that doesn't mean you don't use one of those platforms. Just simply, you're not going to pick it because it has audio processing if you don't have a requirement that needs audio. The other issues, of course, since a lot of these open source development tools are available, even the boards are available as open source, then we have a lot of flexibility. We can tweak the environment. We can tweak the boards to do exactly what we want them to do. There are fab houses, silicon fabs out there, surely, but there are board houses that'll spin a copy of the board for us, and they'll do one panel. So we don't need to spend thousands of dollars to do a run of a printed circuit board. We can put the Gerbers, get the Gerbers off the open source community, put them into our CAD, spin a new copy of the board, send it out to one of these board fab houses, and they'll turn it around within a week. And we'll have 5 boards, whatever happened to fit on the panel, and we'll then have the opportunity to then start stuffing it and getting it ready to actually do some testing. So we have a lot of options available to us. Whether you use GCC or Clang, the LLVM compiler, that's entirely up to you. You will find that there are more examples, worked examples out on the internet with using GCC. There are a few of them that use Clang and LLVM, but again, it depends on what you're really trying to accomplish. Realize that one of the major reasons why you would use LLVM is because it's a faster compiler, but that makes a big difference on something like the Linux kernel, which is thousands, actually is like 16 million lines of code, but an IoT application is usually 1,000 lines of code, maybe. That would be a very large IoT application. So when we're talking about these small processors, the sensors, the integrated distributed networks where we're actually placing, humidity sensors on the vines of the grapes out in the middle of the grape field to find out whether we need to turn on the water. Those are the big kinds of places where we'll see thousands of devices, millions of devices sold, and they're all very small. Now, when we talk about security, and I'll have a session that's going to be on Wednesday on the security piece, you realize quite quickly that any of these distributed sensors, they will be compromised. You have to assume that they will have somebody gain physical access to the sensor. Now, if they gain physical access to the sensor, what does that mean to you? How do you protect the code? How do you protect the sensor? How do you protect the network? All of those things have to be taken into account when we're starting to do a large-scale IoT deployment. So the big key here, though, is the search engine is your friend. Take advantage of what's out there, and hopefully your Google foo is sufficient that you'll be able to find what it is that you're looking for. Of course, in the meantime, we do have some real simple little examples here. Here I have a copy of Eclipse up and running, and this is one of the platforms here. Let me just go ahead and I'll create a new project. Hello. There we go. New, let's see, C++ project here. And then we will see that there are a number of projects out here. I happen to be running the STM32F4 discovery board. So we'll give it a name. We'll call it ELC. Sure, why not? And then we'll specify what kind of processor we're using. So they have all of the Cortex-M processors for that particular manufacturer already defined. So we picked the one that we happen to be using, and I think mine's a 407. We have how much flash we have. It turns out that my board doesn't have 1024. It's only got 512 kbytes worth of flash. The external clock is, I think, still running at 80 megahertz. And we have here a blinky LED content, or we can add an empty project. Again, this is focused on running as bare metal. So this is a freestanding environment with no POSIX system calls associated with it. So there's no RTOS here. This is just bare metal. We can then go into all kinds, there's lots of variants here, a POSIX-based OS. We can have semi-hosting with POSIX-based calls, lots of different issues there. And then the debug channels, we have semi-hosting, standard out, semi-hosting debug channels. We're going to be using a semi-hosting debug channel, and then we'll click next, and then it's asking where's the include file directory, where's the source directory, etc. We'll go ahead and accept that. We have two different versions that we're interested in. We're interested in a debug version. Obviously, it has the debugging target code turned on, the GCC-G option turned on, and then the release version, which doesn't have the debug code in it. So we'll go ahead and click next on that, and it's asking for my tool chain path. So my tool chain path is going to be squirreled away down inside of my system here. My tool chain happens to be in the op directory, and it is ARM EABI 4.9. So this is the GNU 4.9 compiler. We'll click OK on that one, and then click Finish. And basically, that's all I needed to do to create a project which will then have everything in it to be able to be compiled and downloaded onto the board. So here's my ELC. Let me just go ahead and close out a couple of these other ones that I had opened up here. And Blinky there, and there, close that one. We open up the ELC project. There's the source. There's my blinkled.cpp. It goes out, and this is one of these cases when you're dealing with these very small processors, you're going to have to know how to read data sheets. There's just no way to avoid it. You're going to have to be able to read data sheets. So it says you're going to have to go to the manufacturer. You're going to have to get the data sheets somehow. In many cases, for boards like the ST32, it's easy. They make it part of their normal distribution. But there are going to be manufacturers, Marvell and several others, that make it about as difficult as they possibly can to provide you data sheets. You'll have to sign NDAs, you have to commit to 10,000 parts, yada, yada, yada. It kind of gets a little tedious after a while. But the reality is that once you have all that in place and you've figured out, like for instance, how do I get access to the LEDs, then you can go, okay, that's cool. Let me go ahead and I will do a clean. Let's see if I can do it here. Go to the project and then do a clean project. It will then diligently go out and invoke the compiler and do a make clean. And then we'll go ahead and tell it to compile. Go ahead and build the project. And runs the compiler. We see that it's compiling for the Cortex-M4. It's flashing by real quick there, the M CPU, Cortex-M4. And then it will dutifully produce the output and then convert it into the necessary format to be downloaded onto the board, whether that's ELF, whether that's binary. Does it have ELF headers on the front of it? Does it hex? There's lots of different formats that we may potentially see, including S-Record. We still see some of them that use Motorola S-Record format. So once we have it, then we would then tell it to go ahead and run it on the platform. And then when you run it on the platform, it does little blinky LEDs. So it's just a quick example of being able to get something up and running without having to spend a lot of time to do so. And the major issue here was just how much time you spend downloading the code. I mean, downloading the GNU compiler, if you got a fast link, it doesn't take very long. My link at home is an 80 megabit per second symmetric link, and it does a really nice job at downloading most of these things quickly. But if your link isn't quite that fast, then obviously it's going to be limited to what you can do. So we have just a couple of minutes here for questions, and then I actually have the next presentation also in this room. Yes? Yes. Yep. Yes, it supports the ST-Link, both V1 and V2. So he was asking about the debugger interface. It turns out that ST Micro has their own debugger interface called ST-Link, and it does in fact support both ST1 and STV1 and STV2. Most of the new boards are all STV2 anyway. Question? I'm sorry, what was that? Oh, Automake or SCons. You know, Automake is tried and true. It's not necessarily the fastest solution, nor is it necessarily the best, but it always works. Or at least in my experience, with even if you have a problem with a couple of small tweaks, you can make it work. So Automake, it's just how you do the builds and things of that sort, and Automake seems to work fine. Okay? Thank you very much. I appreciate it.